Hi everyone. Going to kind of take a look at the Molar Volume lab. This is all done on pivots. Make sure you go over the pivot to complete this one entirely there. Okay. Now, I have downloaded the experiment. It's kind of a new one this semester, so I'll kind of go through it with you. Okay. So, obviously what we're going to do is we're going to find the molar volume. Let's just remind ourselves what that is, right? So remember, 1 mole any gas equals 22.4 liters at standard temperature and pressure. Okay, so it's really a conversion factor. It's how many liters in a mole, right? So therefore it's kind of a conversion factor, 22.4 liters over 1 mole at standard temperature and pressure. Standard temperature, 0 degrees C, 273 Kelvin, pressure 1 atmosphere. Okay, so if we want to figure out the molar volume, we don't have to make it 22.4. All we have to do is get the number of moles of a gas divided by, sorry, my mistake, the number of liters of a gas divided by the number of moles of a gas at STP, and that ratio will be 22.4 to 1. So, you know, if you've got more, it might be 44.8 to 2, but it's the same ratio, right? So all we're going to do in this experiment, you know, keep your eyes on the prize, is we're going to figure out the volume of a gas under standard conditions, the moles of gas under those same conditions. Just divide those two numbers out, boom, should get close to 22.4. So I'm not going to grade you on accuracy on this one, right? So you might get a little bit higher, might get a little bit lower. That's okay, all right? But you're going to be close, all right? So as long as you're in the ballpark, you can get full credit. I think, you know, the numbers are the numbers. Whatever they give you is pretty much how close you're going to get. All right, okay, but I'm looking for, you know, procedure, so make sure you show all work. So that's the basic idea, yeah, okay. I'll put this little cheat sheet to one side and talk through the experiment with you a little bit, okay. So what we're going to do, and, you know, I'll go back to the cheat sheet as we go. So we're going to observe the production of a gas from a chemical reaction. And that chemical reaction is actually down here, all right, we'll talk about it in more detail in a second. Okay, so we're going to mix some acid with a metal, produce some hydrogen, fair enough, yeah. Now, you know, because of balanced chemical equation, you can figure out moles of product from moles of reactant, so we'll do that, okay. So record the necessary data, we'll talk about that as we go through the experiment, and then calculate molar volume. Again, you're not going to get 22.4 and 1, you're going to get some number for liters and some number for moles, and then divide them to get 22.4, okay. All right, so now it talks about the things we just talked about. There's our experiment. Okay, so we can do a slides and ladders for this one. Okay, so as we go through, and I think, you know, we'll see it as we go. So I'm just going to summarize your experiment. Let's just do that, right? So before we look at the details, let's just summarize your experiment. You have a container, some kind of flask, right? Okay, and then you have Mg plus HCl. Let's get the equation right. 2 of those turns into MgCl2 plus H2. Okay, so, and that gas goes up into here. Okay, so we're generating some gas and we can find the pressure of that gas in a fixed volume. Okay, so we're not finding the volume right off the bat. We're going to have to do a little bit of conversion, right, along the way, but that's our experiment, yeah? Okay, so if you think about it, Mg, solid, plus 2HCl, and that's going to be excess, aqueous, turns into MgCl2 aqueous plus H2. So moles of Mg is the same as moles of H2. And that's the trick, right? So all you do is, if you've got grams of magnesium, molecular weight, grams and moles, all right? So moles is grams over molecular weight. Okay, so take the mass of magnesium, divide it by the molecular weight of magnesium. I think it's somewhere in 24, somewhere around there, right? Let's look on the periodic table. That gives you the moles of magnesium, right? And then that completely reacts to give you the same number of moles of hydrogen. Okay, great. So we know how many moles of hydrogen are in here. That's NPV equals nRT. Okay. All right. So if you think about it, back to our original equation, liters over moles, we got moles already. Okay, so the moles of hydrogen equals the moles of magnesium. Moles of magnesium is grams divided by molecular weight. Okay, so in the Prelab, let's just talk you through here. So as we mentioned in the Prelab, they have a fixed volume container. And the volume is 149.40 milliliters. Okay, that's the volume of the gas. The volume of the gas is the volume of the container, remember. Okay, now the more gas you make, the closer the particles will become and the pressure will go up. Okay, so the more moles, the higher the pressure. It's proportional. All right, so let's look here. So mass of magnesium, fair enough, right? Volume of hydrogen is the number we had, okay? Then initial pressure, now this is where it's interesting because there's a pressure probe here, right? Okay, there's a pressure probe, pressure probe, okay? So record the initial pressure, which is going to be right around atmospheric pressure, remember 101.3, let me write that down, 101.3 kPa equals 1 atmosphere. You're going to need that conversion later, okay? All right, so if you went from 101.3 maybe up to 106.3, you went up by 5 kPa, right? Okay, so you work out the difference in pressure. Yeah, that difference in pressure is the pressure of the gas, isn't it, if you think about it? Okay, makes sense, yeah. All right, because pressures add, yeah, pressure of air plus pressure of hydrogen, subtract the pressure of the air, which is the initial. Initial subtracted from final gives you the pressure of the gas. Okay, so let's talk through your questions and calculations. Calculate the number of moles of magnesium, did that already. Use the slides and ladders, or just do a simple like chain conversion. Grams to moles for magnesium. 1 mole of magnesium makes 1 mole of hydrogen. It's the same number of moles, whatever it is. Okay. 2, calculate the number of moles of hydrogen. Just did that, right? Okay. What's the pressure of the hydrogen collected in kPa units? Okay, so it's just final minus initial, yeah. So if you think about it, when I have that flask, there's already air in there, isn't there? Okay, and then the pressure of the hydrogen adds to the pressure of the air. So final, air plus hydrogen, minus initial, just air is just the pressure of the hydrogen. Okay, now, if it asks you to do it, do it. If you want to do it for extra credit, do it for extra credit. But if you look in the notes, this is what we call a wet gas. Okay, now there's no mention of that in the questions here, calculating the actual pressure of dry hydrogen. But if you want to do it on the side for a little bit of extra credit, you may, but you don't have to for full credit, okay? So if you want to look back at the whole collecting gases over water thing in the notes, you can. You get a slightly more accurate answer, but it's not, it's not too different than the final answer. So, what's the pressure of the hydrogen gas collected? It's just the difference, right? Okay, and if you want to make that wet gas correction, you can, all right? Atmospheres, remember, 101.3 kPa is 1 atmosphere. What's the temperature of the gas? Well, if you know the room temperature, that's the temperature of the gas, right? So it's not at standard conditions. If you record the pressure of the gas and the temperature of the gas in a lab, it's probably going to be different than 0 degrees C, 273 Kelvin, and 1 atmosphere, right? Perhaps, right? So, make sure you get the temperature of the gas, right? And this is going to come into, as we see in a minute when we do, the dynamic version of the ideal gas law. We can change to what it would be under, standard conditions. All right, so what's the temperature of the gas? That's the same as the room temperature. Make sure it's in Kelvin, right? Make sure it's in Kelvin. Okay, now, here's the combined law, right? So STP, right, we call that condition 1, or let's call it condition 2, right? So P2 is 1 atm, that's STP pressure, right? Okay, T2 is 273 Kelvin, okay? And condition 1 is your experiment, all right? So that's experiment, and that's STP, all right? So we can change, and obviously our goal is V2, right? Our goal is to find V2, which is the volume of that many moles. The moles doesn't change, right? Mole is not dependent on pressure or temperature, right? Okay, so we're going to find V2, which is the volume of that number of moles of hydrogen, right, at standard temperature and pressure from the experimental conditions. So whatever the pressure is, temperature and volume, well, that's, you should technically put it in liters, but, it wouldn't matter in this conversion, but I would suggest putting it in liters because, liters is liters per mole, okay? So, 0.149 is 149 milliliters here, yeah? Temperature, lab temperature, pressure. Remember, that's the pressure of the hydrogen, right? Not the big number, the difference number, okay? All right, then, just simply, if you remember back from our initial kind of cheat sheet, having found V2, that's the volume of H2, right? We then make sure it's in litres, divide it by the moles of H2, we got same as the moles of magnesium. Divide them out, bang, that's your answer, right? It should be right around 22.4. Again, it's not going to be perfect, but it doesn't matter. I'm not grading accuracy, okay? Then, you know, hey, how close is it? That's kind of a question, right? So, experimental, whatever number you got, known value 22.4 over 22.4 times 100. So hopefully, now don't go with it. So some people just do a fraction times 100 and they get 95. No, it's not 95%. Right, it's 5%, isn't it? It's a 5% error. It's the difference, right? So it's the experimental minus the known over experimental. Sorry, experimental minus known over known. So your number from the previous question, minus 22.4, is a small number, hopefully, right? And then that number divided by 24 is like a fraction of 22.4 times 100 for a percent. Okay, possible sources of error. I think I mentioned one, right, to do with the water vapor. Okay, so you might want to look back on the notes for that. Okay, hopefully that makes sense. Any questions, you know, discussion area or water cooler chat? Okay, so I'll just leave that there for you to take a quick look at. Okay, so on the whole, a nice lab. We do something quite similar in the regular semester, which is one of the most fun experiments. So unfortunately, you don't get to see that, but you know, this is actually quite a nice experiment, in my opinion, as far as virtual experiments go. All right, stop there. See you next time.